Hello.
Hi, Marcus. How are you? You made it.
Let me turn on my camera. So it seems that my network connections, at least right now, are okay.
Yeah, let's not jinx it.
I had problems, so let's see how that works. Let me see if I can share my slides, if that works. Do people see that? Yeah, no?
Yes.
That work. Okay, very good. I'm still missing one of the slide sets. That's a bit unfortunate.
Only one that's not terrible. Which one? Let me cross-check that I didn't hear anything from them.
Let me see. It's in my notes.
These agendas were all done by hand, so they're not 100% reliable.
Yeah, the talk I'm missing is by Daniel Mournain. It's the graph neural networks for track finding. That is what I still expect to get for the session today, and I didn't get anything. And I'm just checking all the time if it happened, if it's been uploaded. I also don't see him online. Or are you online? No, I don't see him.
So I don't have anything in my inbox related to that.
Okay.
This may be a first thing in the morning West Coast time issue, though. Let's see. But good, if you got all the others, that's great.
Yeah. The rest I have. I hope I have the latest versions, but I mean, people should scream if I don't. Okay. Let's see how that works. Okay. I see that people are still connecting slowly, so we should maybe wait for a few minutes and then start. Very good.
We are 25 now, Marcus. 26. I think that's a really good count. You're muted, Marcus.
You're absolutely right. I'm muted. And I was just saying, and I mean, people are slowly still dropping in, and I was planning to wait for another minute or two before I start. So let's give people another minute or two, and then we start. We are back on 26. Mm-hmm. So it's 3 minutes past the hour. I propose we start. So this is the second session of the Connecting the Dots discussion meetings, where we will discuss the talks, which were, most of them were recorded last Tuesday. And we're going to follow the successful approach which we've taken yesterday. Thanks, Andy, for figuring that out. And what I did is I collected in a set of slides all the introduction slides, which everybody, the summary slides, which everybody was sending to Indico in the order which I took from the session last week. And so the idea will be that we will, like yesterday, bunch a couple of the introductions where I would ask the people to actually turn on their camera and briefly go over their slides to introduce the discussions. And after 3 or 4 of them, we will pause, and then everybody will be able to ask questions, and and then afterwards we will continue. Somewhere in the middle of this, we will make a short break to do the virtual photo, which Andy will take. For that, I will also ask everybody to turn on their cameras so that we see all the faces and can collect them. Are there questions or comments concerning the session and how we would do this? Or is somebody constrained in time and we need to allow the person to go earlier or something? I take that as a no. So let's start with the first set of slides. So the first talk we like to introduce is by Kim. I see your camera. Just go for it.
Thank you. Thanks also for adding my name to the top there.
Yeah.
So we were looking at doing event classification for targeting a trigger application and skipping a traditional track and vertex reconstruction step. So directly doing machine learning classification on the raw detector hits. And we are currently investigating graph neural networks as the machine learning method to apply here. And we use this in a simulated environment with an atlas-like in a detector simulation. And we do some investigations across a number of tasks of increasing complexity and a number of physics processes of increasing complexity. So you can see an example of this to the right, where we consider an electron-positron training for a SUSY process, trying to identify displaced events, so an event containing a displaced vertex, versus prompt events. And here you can see that we do retain some efficiency, even though it's a much more busy environment as we go from the electron-positron sample to the proton-proton environment. But this does not scale infinitely, so with pileup, the efficiency goes away. What I'm not showing here is the more interesting task that tries to tease out if we can find a particular kind of displaced decay, but here we need to refine the training setup. So we are considering doing all the training. So the trainings I showed were all for electron-positron, and we need to tune the setup to do the full training in the proton-proton environment. And then we also need to tune the model parameters, and in particular, increasing the model complexity. And when this is done, we consider running the simulation in a more realistic environment, essentially. Thank you.
Mm-hmm. Thank you. Thank you. The next speaker is Simon. Are you online?
Yes, hello.
Can you turn on your camera? I don't see you.
Yeah, just a second. All right.
Yep, here you are. I like the virtual backgrounds where suddenly people are appearing. Okay, go for it.
So yeah, I had a presentation about the performance of the BEL2 tracking on collision data. In BEL2, we have a combination of 3 tracking detectors for excellent tracking performance. Yeah, a typical epsilon 4s event that we want to analyze consists of about 11 tracks at quite a soft momentum spectrum, and we want to be able to reconstruct all tracks down to a momentum of just about 50 MeV, and that in an environment where we have 2 orders of magnitude more background than actual signal hits. Yeah, to do that, we have quite a modular tracking framework that we're actually quite proud of. So we can adopt the track finding chain to the background conditions, the detector degradation, etc. And it's also quite easy to extend it with novel approaches. Performance-wise, we observe a consistently high track finding efficiency. We're running very stable on the high-level trigger, and the algorithms that we implemented are very robust against the beam backgrounds that we have. Monitoring and validation-wise, there are a variety of tag and probe studies for different momentum regions, and all in all, we observe an excellent performance of our detectors, algorithms, and also the alignment. And one of the benchmark results that I showed you there was the impact parameter resolution that we determined to about 12 micrometers. And then coming to more or less the highlight of the talk, to one of the first really track-based analysis, where we try to determine the D0 lifetime, which is really an excellent exercise for all the tracking. And the result confirms the excellent track resolution and also good understanding of all the systematic effects that can bias our tracking. In any case, more details can be found in the BEL2 tracking paper. I put the archive link on the bottom. Yeah, thanks.
Hey, very nice. Thank you very much. So the next talk is, let me just check. I didn't put the name on the slide. By Marco. Marco, can you
hello,
turn on your camera? And, okay, go for it.
it's on. Okay. So I reported the progress towards a 4D tracking pixel detector that is developed in the TimeSpot R&D project by INFN in Italy. It consists of several working packages. In between, there are the 3D sensors development that achieved 30 picosecond resolution or even less. The design of front-end electronics at 28 nanometer with 28 nanometer technologies, and real-time track reconstruction. That is the main topic of the talk. So, about the 4D fast tracking device, we implemented a demonstrator in FPGA with a parallel and pipeline architecture that is based on the identification of stubs that are hit doublets in adjacent planes to be applied in an LHCb Velo-like detector that has been studied as a case study in upgrade 2 condition that is of LHCb, that is basically RAM4. And also we included the timing information in the path recognition. So we implemented all the system in FPGA with a low latency budget that is about 1 microseconds that needs to, it can be considered as a trigger solution at 40 megahertz event rate as a result, let's say. That's basically all.
Hey, thanks very much. Okay, very nice. Thank you. And I think we should take a fourth one. Fabian, can you turn on your camera and then just tell us about the summary?
You can see me, you can hear me?
Yeah, I can hear both.
All right. Starting from the scenario that the high luminosity LHC will provide up to 200 pileup, we saw that the current inner detector in the Atlas detector is not built for this scenario and will be therefore replaced by the inner tracker. Having a preliminary extrapolation for the CPU consumption, which is shown here in the top, shows that this will become a challenge for tracking. The ITK, together with the some modifications in the current reconstruction software, already showed quite some significant improvements. In order to reduce the CPU consumption, there was a prototype study performed called the Fast Track Reconstruction, which was a CPU oriented optimization of the classical tracking based on mostly modifying the existing workflow. Therewith, we achieved a speed up of roughly a factor of 8 in this phase 2 scenario compared to the current run 2 scenario, concluding therewith that the common tracking will not dominate the CPU consumption anymore. The thereby achieved physics performance is mostly in a good agreement with the default reconstruction. However, we see that the efficiencies for the reconstruction is reduced, as well as we see some parameter resolution losses. This was a consequence of the modifications and approximations that we applied. But on the other hand, we understand the sources of the losses and can fix them in the future. The physics performance that we have definitely requires some improvements in order to be applicable for offline reconstruction. And this is why ACTS will become an essential part for phase 2. As ACTS is an ideal R&D platform for all kinds of track reconstruction algorithms, and it will become beneficial to all kinds of special reconstructions like mu, gamma, b-tagging, and so on. So that for phase 2, ACTS has to deliver the required physics performance for Atlas.
Okay, thanks, Fabian. Thanks very much. I propose we stop here and we start from the beginning again and take questions. The first ones are for Kim. Kim, can you turn on your camera just for the discussion again?
Oh, sure.
Yeah. So if you have questions, raise your hand or just speak if nobody is doing otherwise.
Hi, this is Moritz. So my question would be, for if you're using these graph networks on the raw data, I suspect they become quite large. So what's the kind of, my apologies. What's the kind of memory consumption and performance that you expect to do that, to do this, for example, for going to mu200?
So that, I think you can look at what the ExaTrack project is doing. So I don't have any concrete numbers directly on the top of my head for this. But they already in the HepTrack-X project, I think they had to split up the graph, and they considered the HL-LHC data well, the TrackML data set, which is then similar to it as far as I understand. And they considered splitting up sections splitting up the detector into different sections to reduce the size of this graph. However, there is one, this is speculative at the moment, but if you represent these graphs as matrices, they become very large, yes. But if you do sparse operations, you could potentially also decrease the required size, but then you need to have the entire training and evaluation pipeline implemented with the sparse operations, and it's not clear at the moment if you can do that. So there are ways to mitigate this, either by losing the granularity of the graph or very potentially using a different set of operations.
Okay, I see there's one hand raised. Xiang Yang, do you want to?
Yeah, I have a question concerning your workflow. I'm wondering, like, how do you convert the Atlas data to the graph as the input for your training?
So how we convert a set of hits to a graph?
So did you use the Atlas software framework to generate those events?
No, so we use a combination of Pythia and MadGraph and Delphus to generate a separate simulation environment and events. So we generate our own detector hits, and from that we generate the graphs then. So it's separate from the Atlas reconstruction software at this point in time.
Oh, so then the output will be like more similar to the TrackML dataset, like you can be a text file or something.
We use root files, very similar to what Delphus produces. Yeah, it's a slight modification from the standard Delphus output.
Oh, okay.
Yeah, and I mean that would actually be my question. I mean, how much work is it to go from the kind of toy simulation you are having to tracking ML or some other more realistic detector? I mean, is that in the process of development, or do you foresee bigger problems?
I don't foresee bigger problems, but that is not the current focus. We want to show promising results, like solid results in this setup first, and then we'll consider the transition. But I don't foresee that being a problem because the setup is quite agnostic.
Okay. I mean, it's not that in your simplified setup you are and you're also making use of some of these simplifications. You haven't, or you haven't checked that yet.
So I can't say for the complete discussion here, because I haven't looked that deeply into it. But we operate essentially on R5 Z positions, and if you have this in some sense, then you can plug it in. Then of course you might require tweaks to fully integrate it, but we start our derivation from a collection of 3D point hits.
Okay, are there other questions?
Just a quick comment. So we are in the process to a little clean up the TrackML writing modules. So we have integrated them into the ACTS core stack now, and we try to run a bit longer term project to make the output writers such that they can be used quite easily and a bit more encapsulated, such that people who want to use the TrackML format can find an infrastructure to write it and feed it in from whatever, either their experiment output or from their toy simulation, such that one can also use the TrackML Python library to load it back in, and it's a bit interchangeable.
Okay.
So sorry, just to from my understanding of your comment here, so you provide an easy way to incorporate data generated outside to align to the format that you use for TrackML. Was my understanding right there?
Yes. So what we have is we have a Moritz actually should answer that. He has sort of cleaned up already quite a bit the way the data formats that then is stuffed into the TrackML writers. And what we try to do is make it such that there is a writing module basically which you can use to feed in a very easy structure event data model, feed in your simulation, and it spits out TrackML dataset format, and then from the TrackML we have the Python libraries to read back in this format, which a lot of people have already been using.
So you could actually use that to generate an TrackML dataset with displaced vertices.
Yes,
I mean that's the idea.
You can, and wherever you include ACTS, you could use it to write out TrackML data if you do this small conversion internally. So in TrackML lookalike data,
precisely,
make it easier to put this developments back into the experiment framework.
It's a very nice comment. Thank you for sharing.
Okay, are there more comments or questions before we move on? No. Thanks, Kim. So let's move on.
Thank you.
So then, Simon, can you turn on the camera and we take questions for this talk? And then let me start. I mean, did you turn on your camera? Because I can't see you.
I did, yes.
Okay. No. I mean, somehow by the magic of Zoom, it's reordering things and you're getting in and out. Okay. Anyway, I mean, this is what it is. And when looking at the talk, and I was curious. I mean, the CPU time for vertex finding was actually exceeding the track fitting.
Yeah.
How comes? I mean it's not really on the core of what you've summarized, but I was just curious to learn. I mean, what's going on there?
I wish I could answer that, but I'm not really in the vertex finding business. I honestly don't know.
I mean, it's probably more than just finding the primary vertex, but it's probably doing the decay change, which is why it's taking so long. Huh?
The decay chains are usually reconstructed at analysis level, so this is not part. This is not being done on the HLT, or this is not part of the standard reconstruction actually.
Okay. But that is even more mysterious.
I don't know right now.
Okay.
Sorry.
Okay.
Simon, I have another question if I can
yeah, go for it.
jump into this. You did not mention in your talk, as far as I remember, many details about the alignment procedure. So I see you achieved the excellent the impact parameter resolution of 12 micrometer. Do you know by chance what's your contribution of the alignment on top of that, or no, included in that? I suppose so. So do you have a feeling what would be the optimal resolution with a perfect alignment?
Yeah, so having perfect alignment, we could get down to 10 micrometers. This is as good as it gets.
This is what I wanted. This is what I wanted to understand how far you are already in understanding your detector alignment. So that's actually quite nice. Yeah.
I mean, it will still get a bit better because on the one hand, we don't have the full second layer of our pixel detector installed. So right now there's only 2 ladders, so 4 modules of the second layer of the pixel detector. This will improve the resolution a bit, but it is mostly driven really by hits in the first layer of the pixel detector, and that is just 1.4 centimeters away from the IP. And yeah, so this is for like an average, your typical epsilon 4S event with 11 tracks. If you go to BABA events with only 2 tracks or so, the vertex resolution is of course a bit worse.
So your alignment contribution is around 4 micrometers, 4 or 5 micrometers. That's already, I think, quite astonishing. Yeah.
Yeah, I mean, we're still working on that, right? So there's the University of Prague is working on that quite a lot, and we are confident that we can still improve the values that we have right now. And yeah.
Do you happen to know, off the top of your head, the beam size which you have achieved so far in the machine? I mean, it's presumably not yet the final squeezed the beam size which you need for getting really high luminosity. But
yeah, so we have to squeeze it even further, which we cannot do at the moment because beam backgrounds are very high, and if we squeeze it even more, the background level will just increase by too much. So there's still a lot of investigations and optimizations of the machine going on. The beam spot right now is in the, I think I showed a figure on my talk. So in the vertical directions, it's about 5 micrometers, and in the horizontal direction, about 15 micrometers. And the focusing in the vertical directions will still, get more narrow. So the beam spot, will be even focused more sharply.
Okay. Okay. Are there more questions to Simon? No. Thanks very much. You can turn off your camera, and we go on to the next talk. Marco, can you turn on your camera again? And
yeah, it should be on.
This talk is open for questions. One of the things is, I mean, this is a proposal for the phase 3 upgrade for LHCb, as I understand it, right? I mean, it's in the talk. I was wondering, I mean, what is really the luminosity and pileup scenario and the physics scenario which you would open up with this technology?
Okay, yes. So this is going to be the so-called upgrade 2 of LHCb that is basically the, say, RAM 4. So the pileup is estimated to be about 50 in LHCb, and luminosity is 10 to the 34 because of the leveling in the LHCb is in any case lower with respect to the other LHC experiment, but is still a factor, let's say 5 more than the expected.
Then what will happen in 1.3? Okay.
Yes.
And do you have simulation results actually demonstrating that this will be good enough to separate the events?
Yes, I mean the simulation now are not based on the official LHCb simulation, is some toy simulation, but we are working on that in order to demonstrate that it's feasible for LHCb, because this is a standalone R&D project, but of course we want to set on some experiment if possible. And yes, it results that the efficiency of this algorithm and this device is in any case high, let's say about 98–99%, but the timing is still let's say, is very needed, because in the first case, let's say without including timing, we have about 40% of ghosts, and this number can be reduced at least to 20, but probably even more.
I see that there is a...
yeah.
Sorry?
Sorry, go on.
No, I didn't want to...
Yes, and I mean, the timing is used in this case both for suppression in the identification of doublets, but also, I mean, the really need of timing in the experiment is for evaluating the time of the track for primary vertex finding. That is not discussed here because it's not been studied in this context, but in general in LHCb is a known fact.
Okay, I see that there is one raised hand. David, go for it.
Yes, hi, Marco.
Hi.
So following up on that, so these sensors I know have very short drift distances. What is the intrinsic timing resolution? Do you know? And would that be a useful contribution, the time itself as a tracking parameter, not just pattern recognition and track association, but also in the fits?
Sorry, can you repeat?
So I know these 4D geometry pixels have very short drifts. So intrinsically, I guess the detectors have very good timing, or could have if they were instrumented as such. What is the intrinsic timing resolution of the device? Do you know?
I mean, the results from the test beam of last year demonstrated about 30 picosecond resolution. On the detector itself, on the sensor itself, that was read out using a scope, basically.
That's about like nowadays like the LGATs, right? I mean, this is. I mean, the LGATs are also supposed to get 30-35, which Atlas and CMS are installing.
Yes, but I mean, here the point is. I don't want to say something strange, but no, for example, in the HTDG, in the Atlas, the pixel size is, let's say, a bit, it's about the order of millimeter, correct?
Yeah.
Instead, here we are talking about 55 times 55 micrometers. That is the actual pitch of the velo. So this is a competitor in terms of pitch and possibility to use as a primary vertex finder.
But in principle, David is right. I mean, if you have so small, you also have very small drifts. I mean, it's the 20 microns or so, which is, I think, is less than what we have in the LGATs. And so yeah, I mean, the hope would be you could actually get better than that in terms of timing. But
yeah,
maybe
I just want to throw a number in there for the FCCHH CDR.
Okay.
The assumption is on pixel size of I think in the worst scenario 15 by 15, so 1.5 times 1.5 micron, a 5 picosecond resolution, which is of course streaming in all ends. So you're still one, say, almost one order of magnitude away. But that was the estimate that Zbigniew has been using in order to sustain enough in-jets resolution. So you have a small enough pixels for 100 TV or jets in 100 TV to resolve the in-jet tracks. And to use the timing sufficiently for the pattern recognition. So that's I think was the ultra optimistic or hyper optimistic target in the CDR, if I remember correctly.
I think David had a second half of his question. Do you want to repeat that?
Yeah, right. I know I added too much in there, but yeah. So the question was whether you use this information beyond pattern recognition to use it in the fit, or have you thought about that? I mean, in principle, I guess this becomes a time of flight counter.
Yes. So in the first part, let's say the very first part of the algorithm is the identification of doublets. So the thing is, we search in some, let's say, geometrical region that are acceptable. For example, the stub should point back to the interaction region. And after we have identified that, we apply a timing cut that is based on the velocity of the particle. So at the moment, it is not using the fit, but there is the possibility because the time of the hits is carried out through all the processing chain. So when we arrive at the, let's say, the so-called engine where the pattern recognition is actually performed, we search for clusters, let's say cluster of doublets that have the same parameters, and we use the geometrical one because we already filtered in timing, but in principle, a more refined fit can be applied, let's say, integrating better the time.
Okay, and I see that Moritz has raised his hand.
Yes. Can you say anything about the radiation hardness of the sensors? Because since these are 3Ds, I suspect that they might be not too bad.
Yes. Okay. In the context of time spots, we cannot say because they have not been tested. But let's say the 3D technology in the Atlas that use the, let's say, columns instead of trench achieved 3 times 10 to the 16 neutron equivalent.
Yes, I know that about the Atlas. I was specifically asking about these ones.
Yes. Okay. So in principle, we should expect the same order, but we cannot say.
Yeah. Because it would be interesting to see how the timing resolution is changing when you start irradiating them, and if you can keep this kind of resolutions, right? Because I mean, for example, the LGAs which we're now installing, I mean, they're not particularly radiation hard.
Oh, okay. Yes. Yeah. I mean, the starting point here is that the 3D technology is not really new, but the timing was not exploited. So the idea is to exploit the timing.
Yeah, no, absolutely. That's what's making this study interesting. Absolutely.
Yeah. Okay.
Yeah. I agree with you. Okay, I think we are done with the questions to this talk. Thanks very much. Okay.
Thank you.
Okay, and the final one, Fabian. I should shut up on this one because I'm co-author on that talk. So, are there questions from the other participants on this talk? Seems to be very clear. 3, 2, 1. Okay. we keep it like.
Sorry, I was looking for my mute. I can ask one about.
Yeah, David, go for it.
I think it's not on the. Yeah, it's not on the summary slide, but on the talk with. Did I miss the impact of sort of fake rate on the changes made to make the fast tracking?
Yes, it's not here. In my original talk I showed quite some performance plots. There was on one slide I showed the number of tracks that we received versus eta, which was slightly reduced compared to the default track reconstruction, and from that plot, one can conclude that we have a reduced efficiency, therefore we have less tracks, but since we have a similar amount of tracks compared to the default reconstruction, we don't see a significant increasement of the fake rate.
Oh, okay. I didn't make that connection in my head. I'll go back and look. Thank you. Yeah.
Okay. Other questions? No? Okay, thanks very much, Fabian. I propose we go to the virtual photo. Andy, can you do this? Andy? He's muted.
I should be able to if you can't.
Yeah, okay. Can everybody turn on the camera? Is that
Yeah,
possible?
it's not actually on. I'm going to turn on now.
Everybody, so that we can take a photo.
Marcus.
Yeah?
I was shifted to this session, so I think you might have missed.
No. Yeah, your talk is coming.
Ah, sorry. Then I forgot about that. Sorry, I didn't understand.
I'm just taking a break right now, so that
No.
Because we are now somewhat.
Sorry. My apologies.
Of the people in the session, and we want to keep your camera on because we want to take a photo of you. Okay, David, do that as well for you.
One of my cameras is on.
Okay. So if you want, everybody needs to smile now, and he's going to take some screenshots. David is muted, so I don't know when he's done, actually.
But so what I can't do is get it into full screen mode, or I can't get the photos into the mode I want.
Yeah, but if you just take the small ones up here, that should work.
You may have to stop sharing the screen. If you stop sharing,
can you do that?
Yep, I can. Let me see how I do this.
Oh, in fact, that's why I can't do it.
Yeah. Okay.
Yeah, there we go. Gallery view. Yeah, I have at least. Well, I got. How many people do I have on my screen? 25. So that must be.
Yeah, we are 35 right now.
Now I can go to now I can go to screen 2. Nobody.
Yeah, somehow we are losing a few. I don't know if people expect that we are ending.
There we go.
We are just.
You scared everybody away. I think I got most people.
Being taken on the photo.
All right. I think I got everybody. It moves around randomly. I don't quite know how this works, but
yeah.
All right, we can go back to
regular
mode now. Thank you.
I can restart the sharing if I find the screen. Okay, looks good. Very good. Thanks very much for everybody helping us doing this. Somehow it lost.
Well, I was just out for the conference photo. 1 minute.
Yeah.
No worries. I'm on it. I'm on one already. So.
Yeah. You're on the yesterday one. So
yeah, I was just a minute out and I missed the photo. That's what happens in a conference. Yeah.
Yeah, exactly. So let's see. The next in line is Christian to talk about quantum track reconstruction for non-HAP applications.
Okay,
can you turn on your video and?
I'm on it, yeah.
Okay, hi. And tell us what it is about.
So it's basically we are ClearNet. We are either working at CERN or have been working at CERN. So we came up with the question: is it possible to map or apply tracking algorithms that are used in particle physics to the world outside of physics? And we found some similarities between the track reconstruction in particle physics and aviation. For example, there's a huge amount of data to be expected within the next years. And there are, as you can see in the image on the right-hand side, if you look on the screen, you can see a very distinctive flight path. So these track algorithms can be applied to help to improve or / answer questions in regards to safety, capacity, environmental questions, as well as cost and efficiency questions. So the usual analysis is done due to the compared to the physics amount of data, not so much data. It's sufficient if you use classical machine learning methods, and because we gather data from various sources, for example, satellite data that you can see here in the plot. But well, as we are or have been sound physicists, we came to the idea to explore if it's possible to apply quantum computing methods to this specific topic, because this might be an interesting topic within the next few years, but not now, of course. But yes, is it possible to do so? And therefore, we found a collaboration between GLONet, CERN Open Lab, Caltech, Meteor, DAISY, and DAISY. And for the physics application, you have heard, of course, Cenk do this talk on last Monday and yesterday in the question session. And the goal of the aviation side is to gain a good understanding of the risks of upcoming collisions, because this is naturally that you would like to avoid.
Okay. Thanks very much. Okay, then we go to the second talk. Moritz, that's you. Turn on your camera, please. Moritz?
Yes. So I hope this works. Yes, so we presented a different way of looking at particle tracking by framing particle tracking as a approximate nearest neighbor issue problem. I'm sorry for that.
Okay. We all tell
where instead of doing a combinatorial search, you built this approximate nearest neighbor data structure, and then pre-select the hits that you have in what's called buckets of nearest neighbor hits, which in our case would be hits originating from the same track. And then you only need to do a local reconstruction within those tracks. And this is a data-driven, detector-independent method that shows promising results for TrackML datasets as well as for the ATK dataset. That's it.
Okay, thanks very much. The next one is Nicole.
Yes, so I'm presenting an application of tracks for B tagging. So this is comparing two different alternatives for how we model the jet. We currently on Atlas do one of the algorithms for B tagging, modeling the jet as a sequence with the recurrent neural network, but this work proposes instead modeling the jet as a set using a deep set architecture with an algorithm called DIPS, and the model architecture is given in the middle of the slide. So on the lower, I show a comparison between training the same inputs for RNNIP and DIPS. So you can see with the same inputs, they have similar performance, but the reason why we were excited was because be able to parallelize the track features over the phi networks gave the factor of 3 to 4 increase in training time and inference time. I showed some additional optimization studies to further push the performance of DIPS. And the last thing I was going to show was investigating what the model had learned in the lower right-hand plot, looking at a saliency map, which is how changing the inputs changes the output of the B tagging discriminant. And this is looking at jets that failed B tagging, and you can see that to make the jet more B-like, you want at least 5 high significant tracks per jet in the bottom column.
Okay. Thanks very much. Okay, then let's. On the agenda there was Daniel Murnane. I don't know if you're online. Are you online? It might be.
I'm here.
Did you upload your slides?
Yeah, I thought I'd did. I'm just looking at it now, and I can't see them.
Yeah, so do I.
Do you want to take questions now? I can upload them, or I can share my screen, or what would you?
Yeah, I mean, what I propose we do is we take you at the end, because I didn't put you in the package of slides because of that, and then we do that at the end, if that's okay with you.
Yeah, sorry, I thought that I uploaded them yesterday.
Yeah, the finger troubles, no problem.
Okay.
Okay, then let's do that. Let's take questions for the talks. So let's go back to Christiane. Can you turn on your camera again? So other questions for her? I mean, I have a naive one. I mean, why is that problem particularly suited for quantum computers, other than that it's interesting to actually exploit the technology? I mean, is there anything which makes it suitable for these kind of machines? Because the number of qubits you have and so on is quite limited, right? And that's quite a bit of data and quite a bit of complexity you're throwing at it.
Oh, well, I mean, you can, of course, decrease the data if you apply the relevant cuts. But yes, it was just the possibility to show, to look, is it possible or not? And I mean, we are talking about of 500 gigabytes per month, so it's nothing compared to what you actually mine. And so so this is quite a few amount of data, if I may say so. And it's just to explore if it's possible or not. And well, especially in the risk of collisions. So at the moment, the aviator has 13 seconds to react when the system starts to give a warning. So in 57 kilometers, you will have a collision. Oh, so you have to react. And the goal is to maybe get the result even a little bit earlier, so that the aviator has a little bit more time to react.
I see that there are more questions. David, I think you were the first one.
Yeah, thanks. So I'm curious what the sensor network looks like that you're assuming in this model. Are you trying to solve this as a global problem, like your picture implies, or is this local? Do you, I mean, somehow you must have some interface in mind. I'm just curious what it is.
Well, at some point in the far future, we would like to go global, but at the moment we are just limited on flights over one country, where we figured out that there are these alerts, so that we can actually test if it's working on the classical side and on the quantum computing side. But yes, at some point, of course, in the very far future, we would like to address this question globally.
Okay. I think the next one was Andy again. Andy?
Hi. Christiane, very nice. I remember when we first discussed this, I don't know, a year ago or something, this project. It did strike to me like that's the origin of Kalman filtering. It's missile projection, right? That's what Kalman worked on. And then we discussed once whether this wouldn't be suitable for if you wanted to have a machine learning technique for an RNN. So did you ever pursue this idea? Did you try to model that with a recurrent neural network, which basically mimics a Kalman filter?
Yes, we did, but we used I'm not sure if you use it from how it's called. It's used at Bell. There's a publication by Tobias Schlüter in 2014. It's applied in pandas as well for the tracking, but I can't remember the name.
Okay.
I don't know.
But it's meanwhile a very common filter, and GenFit. Yes, this is the algorithm we decided to use in the end because it's better performing and more accurate. So and then we applied the
Okay,
neural network.
Write that out. Okay, good. Thank you.
Paolo, you
I
wanted to
actually
ask
have a question which is similar to yours, Marcus, but on a different angle. So this is probably also applies to Senk. Do you guys have a plan or some intuition on what could be the advantage of using, for example, a quantum edge network rather than the traditional edge network, and how would you compare the two? Is there a plan to compare the performance of the two? Is this happening? So I actually didn't look at the other talk, so maybe if that is described there, I apologize.
Cenk, do you want to go first, or?
So maybe I can answer this. In the quantum edge network, we didn't see a really advantage compared to classical. So this was the quantum part was an exploratory thing that we were trying to see if we can build it in a quantum computer. So we can say that there is no advantage of using the quantum edge network, but we can get similar results using the quantum computer. So maybe with more improvements, we can get some advantages, but not currently, not at the moment.
Yes, and for us, it's basically the same approach. At the moment, it's not quantum computing in general is not in the stage where you can say, oh no, I've got this much better performance if you don't have access to a real quantum computer. So
yeah, no, clearly not today. I was thinking if you see a direction like 5-10 years from now or something like that, where this could be. It's okay. Thanks.
Okay. I don't see any new raised hands, only the ones which we had already. Or Andy said a new raised hand.
No, I'm just stuck with my head apparently.
I
found it.
Hand, unfortunately,
I lower it. Sorry, it was virtually hurting already.
Okay. It seems we don't have any new questions anymore. So thanks again. And we move on to the next talk. Moritz, can you turn on your camera? Other questions? I see, Paulo, this is from the previous talk, or is to that one? Okay.
Marcus, did you ask me something?
Yeah, I mean, your hand was still raised? Oh no, it's not.
Oh no, my hand was for the previous talk. Sorry.
Okay, yeah, that was my question.
But I actually do have a question to Moritz. So
yeah, go for it.
It's more than a question. It's a comment that Andy already made. I think during Daniel's recording. I do see a lot of possible connections. In your full talk, you were talking about metric learning for tracks, and I do see that that there is a lot of room for collaboration there between the work that Nick and Daniel have been doing and the work you have been doing with the bucketing and dashing. So I just want to make this comment. No.
Yeah, I agree. I think there are quite a few unexplored algorithmic avenues there, and we really have to thank Sabrina for digging this out.
Yeah. As I promised, I will organize a follow-up meeting between the hashers and the track access. That we can see and sit together because there is so much similarity, but yet a slightly different view angle, and I think it would be really fun to bring all of those at least on the virtual table.
Moritz, I do have a question. I mean, it's the algorithm of the similarity hashing needs to throw the dice. I mean, there's some random drawing. which of course, I mean, in terms of reconstruction, high energy physics experiments hate to do because it spoils reproducibility. What's the solution?
So one of the solutions would be, because you need random projections, and at the moment we generate random projections for each event. That you could just pick one set and see if that works, and then reuse this type of projection. But there you need to verify that it works well enough for all types of events. The argument that it doesn't really matter is more that because you're doing these random projections in a lot of dimensions, essentially, that because you then have a high dimensional object, the underlying randomness doesn't really matter anymore. But I agree, for this particular type of hashing that we used as one of the examples, you need some randomness to roll the random projections. But from what we see, that we're not really sensitive. We're not too sensitive to the particular choice that we do. And then there are other methods available that don't require this randomness. So I agree that in this particular case, yes, it's probably not what you want to do in the end, but I don't see that it is a general issue.
Yeah, I mean, for the new physics event, I mean, of course, some randomness in reconstruction would be a disaster. No? Okay. Any other people to ask a question?
I could ask a question to Moritz. Hey, this is Steve. I think like in your, your hashing and bucketing, you talk about like, you had pretty good numbers in capturing most like complete tracks in your buckets. But inevitably, because this is drawing kind of hard boundaries, there are some that are just sort of cut off, right? I'm wondering like, I forget if you talked about this, so I apologize if you did, but have you looked at kind of the characteristics of the tracks that do get chopped? Is it kind of just like uniformly random, or are they like particularly like low PT ones or anything like this?
We lose, of course, in the low PT region, where the curvature of the tracks makes them go out of the bucket. The term that I think Sabrina coined for that is we want to bend the bucket, and we're working on to see how we can do that. One of the ideas that we had is to see if we can get improvements with metric learning, but that involves a few other steps that we need to do. So the majority of particles that we lose there is low PT, and depending on what you're interested in, it's significantly below the threshold that we, for example, usually use in HLHC studies.
Okay, that's nice.
Okay. Any other questions? Doesn't seem to be the case. Thanks, Moritz. Let's move on. So, Nicole, can you turn on again your camera, and we take questions for this talk. Nicole, are you there?
Yes, I've turned on my camera.
Ah, okay. I don't know what Zoom is doing with ordering the windows. I mean, I keep looking for the people, and you didn't say anything. And I was wondering, I mean, it's the dips, but also the RNN. I mean, it takes a lot of tracking information. How robust is that in terms of systematics? I mean, because yeah, by really getting fancy in using that information with your approach, I mean, you're exploiting it, but is there some instabilities? Are you aware of any of this?
We calibrated, they calibrated the high-level tagger with the RNN recently. and the calibration worked all okay. So it seems to be
That's
okay.
on data. That's on data.
That's on data.
Yeah. So, but you're not aware of, I mean, because it uses things like, I mean, it's not on your summary table, but the input tables also has the number of missed hits and stuff like this, which of course, if I mean, the detector is aging. I mean, and that's also what I'm having in mind. The B layer, which is layer 1 now, is aging and might become unreliable. I mean, how sensitive the performance of this tagger would be. Are you aware of any studies which were actually looking into this?
I don't think we've looked at detector aging with B tagging yet.
Okay, so then that's maybe something to look into. It would actually be interesting to see. I mean, that's why I was wondering. Paulo, you had a question.
I do, yes. Nicola already asked you some questions, but let me ask you one more question. So do you have an intuition why your DIPS is like 3-4 times faster than the RNN when it runs on a GPU? Because it looks like a very sequential algorithm anyway, right? Because it has to walk through the list of possible entries in the set.
So I wanted to show the picture this way to make it clear that the phi algorithm operates separately, but it's the same network on each track. But in practice, the GPU paralyzes this, so you can put it's just a 3D tensor that does the matrix multiplication, so that's why it's faster.
Oh, okay. Good. We should use this.
Yep. Any other questions?
I had one. I decided from your talk that you had a couple of slides about flip tagger, which in the end I decided I didn't know what its physics goal was.
So
can you talk about that?
Yeah, so it's for the light jet calibration, or determining the ratio of data to Monte Carlo on the sample of jets from UC or strange quarks or gluons. And so since the B taggers are so good, you can see in this plot, it's close to 1,000 rejection. That means if you cut on them, you'll have a very depleted sample of light jets. So that's why we want the flip tagger, which has same performance for lights. So that way you have something to calibrate, but then a lot less B jet contamination. I don't know if that helps.
Oh, I'm muted. Yeah, thank you. That answers my question.
Okay, any other questions? No? Thanks again, Nicole.
Actually, yeah, I could ask one, sorry.
Okay, yeah, Steve, go for it.
I haven't watched your talk. I'm very sorry if you already answered this. There's a whole like growing family of models, neural network models now that can operate on, point clouds and things like this, point net type models, and our graph neural network models. Just curious if you tried any others besides deep sets, or you were just sort of pretty strongly motivated that deep sets was a great one to stick with.
So deep sets was the first one that I tried, but I think Jonathan Shlomi has been, he's also on Atlas, and he's been looking into more graph neural network type approaches for this problem.
Okay, cool. Thanks.
Thank you.
Okay, I don't see any other raised hands. Thank you. Okay, let's see. We are done. So let's start with the next batch of introduction slides. This is actually 3 slides. David, just go for it. Turn in your camera when you talk.
Yes, I apologize. I'm very bad at following instructions.
You tell me.
I thought the first one was there just to help you when you were organizing things, but yeah, so just to remind people, this was yet another Kalman filter package, what the world needs now, right? And but the concept was based on centralizing the design around the kinematic fit. So where you've got explicit mass information and time information. The more perhaps interesting coding features were that the parameterization was not fixed. So this is a algorithm where you template on whatever parameterization makes sense for your physics application. And we provided a couple of options with an impact parameter-based parameterization and also something more tuned for long looping tracks that we get in the experiment I'm working on. And yeah, and the upshot, if you slip to the next slide, is that this fit gives us intrinsic particle ID and time direction, so hit direction information. So we're not a collider. We don't have a vertex. We can't go back out from and assume everything comes from that one point. So that's a nice feature for this low momentum region, 100 MeV, where we need very precision tracking for the experiment mu to E that I'm working on.
Mm-hmm.
That's it.
Thank you. Okay, then let's go to the next slide. This is Niklas. Can you turn on the camera?
Yes. So basically, for this work, a lot of the different approaches in particle tracking, specifically we're looking at TrackML data, they involve a stage for building doublets. And the way that these doublets are typically built, whether they be for more traditional pipelines or for graphs and graph neural network approaches, is to use just some physics-based cuts to group together pairs of hits that are likely to belong to the same track. And so the idea for this work is, can we instead learn a metric on those hits so that we can kind of do this with a machine learning approach. So the pipeline over to the right is that, well, I guess before I say that, this approach can be extended to looking at triplets or looking at tracklets. One of the main results is for doublets, but the example on the right is for triplets. So the first thing you would do is you would start with a single triplet in the original space. You'll look at the points embedded by the machine learning model in the learned space, and that learned space has a Euclidean metric. You'll find points that are nearby in the learned space, and then in the third image, it's a little bit tough to see, but the yellow points are all the seeds that are nearby to the seed hit, or to the seed triplet of the red hits. And then applying a final filtering to those neighborhoods, we get the fourth image, which actually perfectly reconstructs this track in this case. So for doublets, this approach ends up finding, I believe, about twice as many true pairs of hits. So the purity, or the efficiency rather, is quite high, and the purity is, I believe, about a 6-fold improvement. So something like maybe 5% up to about 30% purity on the doublet graphs for the GNN models that are used later. Looking at triplets, the results from this work, the maximum recoverable TrackML score that we could get from the set of triplet candidates is about 0.82, and using this learned pipeline, this learned embedding pipeline, we can recover about 0.78. So obviously would love to have triplets input that can achieve a little bit better score, but already it's looking quite good. That's it.
Okay, thanks very much. Okay, and then let's go to the next talk. This is, let me see, it's Felix. Can you turn on your camera while talking?
Can you see me?
Yeah. Hi.
Okay. So I talked about first experiences with the neural network set trigger under luminosity conditions in the Bell2 experiment. And sorry, my slide is a bit crowded, but so we're starting with already pre-filtered data from the central drift chamber, which we use then as an input to our neural trigger or neural network. And then we estimate a set vertex for the track. And as you can see here in the bottom, it's very small, but we get around a delta Z resolution of around 4 centimeters compared to reconstructed tracks, with, for tracks from the interaction point, which is quite good. And then the next step is that we want to use this trigger as a for background rejection. So we tried out a limit of 35 centimeters. So we would reject every track that is coming from that is 30 or not within 35 centimeters around the interaction point. And here on the right side, on the right top, you can see the reconstructed set vertex of all rejected tracks. So the good thing is that the background rejection works. So it looks a lot like the original one on the plot left of it, but we also have this huge peak still in the middle at the interaction point, which is not good. But when we actually look at this data, then we see, and we look at the cosine theta distribution, and we see that most of those reconstructed tracks are just not within the CDC acceptance, or in the acceptance of the drift chamber. So our neurotrigger cannot see them, and thus we cannot really do better. However, there are a few tracks left in the middle where this small ellipse is marking them, and those we still need to understand where they come from.
Okay, thanks very much. So I had another discussion break, so let's take the talks then for questions, and the first one is David. People can ask questions if they want to, or raise hands. And I was wondering, I mean, we heard about the LHCb upgrade, we have the Atlas CMS timing, and this is now Mu2E. I mean, is there a case for really coordinating a little bit more in the community these efforts on 4D track fitting and so on? Or you think your use case is so far out that it's probably not going to make much sense?
I guess if I thought there was no chance of collaboration, I wouldn't be presenting a talk. But, yeah.
Yeah, I was fishing for it a little.
Yeah, I mean, I think there were a couple of things that I learned doing this, and so we needed something that worked, and obviously the existing tools out there weren't satisfying us. I think it's useful in drift cell environments where timing and spatial information are correlated, and moving into a time domain for the fit parameterization naturally handles that. I thought I was pleased at how that worked. I've done fits in other ways before without doing, more explicit sort of space to time type correlations. And this was much more natural. And I don't know if there would be applications outside of this, but I'd be interested to hear.
Yeah, I mean, it's for Atlas and CMS. I mean, we only have timing at the end, but the timing might actually give us some additional vertexing constraints if we have correlation matrices right. I mean, so there might be something actually if we have these correlation terms, it might actually allow us to do these kind of things in the track fits. So I was wondering. I mean, ACTS would be a natural place to actually do these kind of things, for example.
Yeah, I've looked through ACT, and to what I can tell, some of what's already built into this structure was used. I mean, there was some common technology as far as I can tell, whether that was coherent evolution or what. I mean, this code was based on Babar code from many, many years ago.
Okay. I see Morris has raised his hands. Go for it.
Yeah, I just want to comment saying that in ACTS we're moving also towards for the parameterizations natively in almost everything. So maybe we should talk a bit more offline.
When you say parameterization, do you mean the spatial trajectory representation?
Yes, I'm referring to the parameterization. So we're moving fully to 8D parameters or 60 parameters, depending whether you do it in full free space or bound to surfaces. So that would naturally include T0 as a track parameter, as well as some form of velocity.
Okay. Any other questions which people like to ask?
Maybe I'll ask a completely different question. So David, I'm trying to understand. I'm trying to understand whether you seem to make this duality between, like, either make explicitly choose the particle mass index on the curvature, or using the n choosing a T0, and sorry, n fitting a T0, or vice versa. Is this the case, or is it possible to fit both the curvature and the time of the track?
Well, curvature and time are somewhat orthogonal. Maybe what you're asking is whether we could let mass be a free floating parameter in the fit.
Yeah, I guess that's what I'm asking. Yes.
Yeah, I've thought of that, and you can sort of get the answer from these plots on the right. You have discrimination power. You do not have selectability. If you let it be a free parameter, you diverge, or you end up with non-physical solutions. Ultimately, I think you want to pick mass is discrete after all, so it makes more sense to just start. There's a small penalty that you pay by having to test multiple hypotheses.
Mm-hmm.
For our application, it is absolutely negligible. I could imagine cases where it's not. But if you needed to optimize, the bar had optimized that, for instance, in that we seeded the next, if you had to do two possible hypotheses or n, you would seed the second and third and fourth from the first, so save most of the iterations. I haven't bothered to do that here.
Thanks.
Okay, I don't see any new hand. Or is that Moritz again? No. Probably he didn't lower his hand.
Sorry, just forgot to lower.
Okay.
Yeah, there should be a timeout on that.
There should be, yes. Unfortunately, there's not. Okay, I mean, if there are no more questions, thanks, David, and we move on. So, Nicolas, can you turn on your camera, please? Very good. So, questions to him.
Marcus, I have questions. Sorry.
Just go for it. Go for it.
Yeah, I don't know how to raise my hand. I see how to clap, but not.
Yeah, it's okay.
Yeah. Anyway, yes. So Nicolas is a very nice talk. And in fact, but TrackML first, when we were discussing with machine learning people, and learning metrics was the idea which they suggested, but I'm not aware anyone has tried to do it and not done it. This is very nice to see. My question is whether you've tried to look at the transformation which was learned and try to understand what it was, whether it was close to something which would kind of make sense in a human understandable way, like a Hoff transform or something.
So we looked at that a little bit, and for the most part, it seems like it's discriminating in the ZR plane with that angle. And then it's doing a few other things. So the input features for each of the hits, we have the XYZ position, and then we also have a little bit of information from each of the cells. So I know there's a little bit more than just looking at things in the ZR plane, but I would say most of the learned space, that's what it's discriminating on.
Mm-hmm. Moritz?
Yeah, now it's intentional. So I would just wanted to ask, you mentioned just that briefly that you're also using some additional information from the cells in the TrackML dataset. To what extent did you use that?
So I'm actually using some features that Zhang Yang had created, but basically looking at the cells for like some very basic direction information. That's how we're using that data.
Okay, because we started doing something similar for the metric learning part, and we realized that the TrackML features that we built are way too optimistic for any realistic detector. Or to put it in the other way, if you would have had a detector that could give you this information, you would be much better off.
Paula is agreeing, Moritz.
I'm sorry, everyone. I'm apologizing for that, but there were conflicts with scheduled meetings between me and Paula's mother. So, yeah.
Can I comment quickly on just clarify on Moritz's comment? The shipped TrackML data, the one which is available and has been made public for the TrackML challenge, does not have the too optimistic angle. So if you use that, it has the geometric cluster sizes which you would expect if a detector didn't have a silicon detector didn't have knockout electrons and has very good readout characteristics. Yeah, let's put it that
That's
way.
what I meant.
Yeah.
This is what I mean. So that the measured charges per cell are way too good.
When we tried even further and used the inner angle computation from this cluster size and determined that early in the reconstruction kind of a mock-up, there we had even better basically stub information, and that's optimistic. However, as we have seen in the CMS talks with the upgraded HLFC detector, once you have stub track information, you're practically there. What you're associating is your hit gets additional angular information. So in any feature learning and in any exploitation of multidimensional features, you will start winning. And I think that's what we see.
Yeah, that was my comment regarding that. We've discussed it before, right? That if you can frame it the other way around, this is an argument for making better detectors that can do such things, because it enables us to do much better reconstructions if we have additional hit features available.
It sounds like you should take that offline with Nicolas and look at this. I see more hands, so I don't know who was first. Was this Mosen? Or
maybe I can quickly follow up to clarify.
Yeah, just follow up if you want.
Yeah. So basically, this cluster information we used is we do not use the charge information, and we just use cluster shape in this deposit in the cells. And we do see we also have some standalone studies. Do see that including the cluster shape alone, not the charge, actually can increase the discriminating power in, for example, seed finding. So I think so follow this question that is this shape is realistically simulated? I think from Andy's comments that the shape of the cluster is more realistic.
Yes, the shape are pretty good actually. We have deployed the same model that is in the Atlas Fast track simulation. That's where the original code comes from, and that has been cross-checked with full sim and has realistic, a bit idealistic shapes. What I said, the main component missing is additional pixels which you would have from delta electrons.
Oh, that's excellent. For our understanding, that this cluster information currently is available, but it's not used.
Mm-hmm. Okay, then there's Mosen who wanted to, who has raised it.
Yes, all right. For the embedding model, you choose the embedding dimension, the M, to be equal to 8. So my question is, how should we select the number? According to what? It comes from the physics side or machine learning side?
So I chose that more from the machine learning side, and basically after the embedding takes place, so the embedding model operating on the original points, that's going to be very fast. The next thing that has to happen is running a KD tree over each event, and that can take quite a bit more time if that embedding dimension is higher. We ran this training pipeline with a few different embedding dimensions, starting from, I believe the smallest we did was about 3, and up to about 8. You don't see much gain in performance after that. So it's basically choose the smallest embedding dimension possible without sacrificing too much in terms of precision or efficiency.
Okay, and I had one question. I mean, you mentioned some pretty impressive improvements by using that. But when I looked at the table, I mean, it seemed like the classical cut-based doublet selection was very inefficient at low PT. Is that just a feature or a bad tuning of what you are doing? I'm just asking, I mean, how realistic are these improvements? Or is the basis just too trivial, and with a bit of tuning you could get it closer?
So I am not extremely familiar with what it went into those baselines. I know Steve had originally run it, so perhaps he could comment.
Yeah, these are my just sort of like, I mean, it's a pretty fair point, Marcus, that these were kind of just like poor man heuristic cuts that were just sort of tuned a little bit to work in our initial graph neural network models. Yeah. Okay.
I mean, they're pretty high efficiency at high PT. Very probably.
Yeah, that was how they were motivated. Definitely, we knew we were cutting away a lot of the low PT stuff, but we're mostly okay with that. Yeah.
Fair point. Thanks. Are there more questions to the speaker? No? Thanks, Nicolas. So let's move on. So this is Felix. Can you turn on your camera?
Yes.
Are there questions for Felix? I mean, I had one. I mean, you have a lot of structure in your data background plot. I mean, is that structure understood, or were there any surprises in what you were seeing there? You know that by chance?
So most of the parts are expected. So this small, you can't see my mouse. Okay. So
no. You have to describe it. Unfortunately, I mean,
yeah. So when you look at the plot next to the Super CAC-B logo, or the Super CAC-B drawing, there is a very small peak at around 20 centimeters, which is coming from the crossing point of the beam pipes of the joining part, and at 50 centimeters there is another part of the structure, This is the bigger peak, and so this is where a lot of background is coming from. And yeah, but I've not looked detailed into the comparison between simulated background and real background till now.
Okay, fair enough. Thanks. Are there other questions to him?
I guess I had one on I think it's the lower right figure on the right-hand side. I guess I didn't understand how important that is in terms of what's the impact on your physics program, I guess, that those false negatives are there. In terms of epsilon 4s events or charm events, is there really any impact?
Yeah, so that's what we still need to figure out. So of course, when we reject something, that's why our resolution is around 4 centimeters, but we took our cut at 35 centimeters originally to be sure that we do not throw anything important. And yeah, those tracks that are left over there, we haven't still figured out what they are exactly and why they are there. This is also data from around Christmas. So in this time, we also had a few problems with our debug output. So usually all of this data is filtered, but who knows, maybe there was some error there. So yeah, we are not really sure yet where they are coming from.
Okay, thank you.
David.
Yeah, a follow-up on that. I mean, it wasn't clear, or at least I couldn't figure it out. Do you think these are physically real particles, or are these artifacts of the algorithm?
I think they are some sort of or they could be some sort of background events that yeah.
I mean, we had backgrounds in Babar coming from the Final Focus quads and some of the shielding that was there, and that was a major effort to get that. But that was single hits. Those were mostly photons coming from synchrotron radiation. But this looks like a track, so I guess I don't know. I don't have a mental picture. Maybe you guys are still working on it.
Can't you just correlate that data with some of the silicon tracker information to figure out? I mean, that should be able to tell you, right?
Yes, that's what's ongoing at the moment. So those are quite fresh plots. So it's I hope in 1 or 2 weeks we know where this is coming from. But yeah, at the moment, unfortunately I cannot I cannot tell.
Okay. Thanks. Are there more questions to Felix, or doesn't seem to be the case? Okay, thanks, Felix. So let's see. I think we are done with that round of discussion. So let's go to the last set of talks. I propose the one where we missed the slides we take at the very end, because I then have to go out of my talk and change the sharing, and I don't want to go back and forth, if that's okay. So the first talk is Joe. Can you turn on your camera?
Yep. Hello.
To the slides. Hey.
Yep. So my talk was about the requirement status and plans for track reconstruction at the S-Phoenix experiment. So S-Phoenix, I gave some overview of S-Phoenix as a dedicated jet and heavy flavor experiment that's being constructed at the Relativistic Heavy Ion Collider. So we will commission this detector in 2022 and start physics data taking in 2023. And we have a very challenging tracking environment due to the large occupancy in heavy ion collisions to begin with, but also the fact that we will have significantly high luminosity in those heavy ion collisions from the accelerator group. So at the moment we are working on reducing our tracking time to under 5 seconds per event in these kinds of environments where we have orders of hundreds of thousands of hits in our silicon and TPC detectors. So we're exploring ACS as a toolkit for reducing this track reconstruction time. So I discussed a little bit about our experience so far in implementing ACS into our software stack. So I just put some thoughts for discussion, maybe to spark some questions or something. I know that there are some other collaborations exploring ACS, for example, Bell2, the CEPC, and also the EIC. And as some of the ACTS talks mentioned, the developer and user base is growing. And we're currently working on implementing some more complex geometries like the S-Phoenix time projection chamber. And I know Bell2 also has some interest in this kind of geometry. So I just put this as a potential discussion starter. Are there other tools that might be useful or other geometries that might be useful? I know there's also a talk about some vertex fitting capabilities that ACTS has been working on recently.
Yeah, there was a talk on that, yeah.
Mm-hmm.
Okay, that's it?
That's it, thank you.
Yeah, thanks. Okay, so let's go to the next talk. Sarah, can you turn on your camera and talk us through?
Yep. So yeah, okay, I've turned it on. I don't know if it's shown up in there.
I like the snow.
All right. Yeah. Well, right. Yeah. I mean, I wish I was there, but all right. Yeah. So okay. Yeah. I'll just go very briefly over this. So the main idea was to help challenging final state topology. So in this case, the use case is VBFX invisibles by being better at telling where they occur in an event. And this is in the context of the Atlas experiment. So conventionally, we just, in a given event, look for the vertex that just had the most visible PT coming out of it in the form of tracks. And then we just say that that's the vertex that the physics that we care about came from. But if we have a final state that is actually, you know, that has a very low visible PT to begin with, then obviously the efficiency of this method will not be very good on that. So what we propose to do is, instead of maximizing this, you know, PT squared emanating from a vertex, instead summing over tracks in a vertex that, you know, only go into hard jets. And then we also have this preferential jet PT factor that boosts essentially the sum PT term for these low PT vertices. And the cartoon on the left really summarizes this idea that, you know, you may have a sort of a soft hard scatter vertex with a few tracks going to jets, which could easily be overshadowed by a really noisy pilot vertex somewhere else in the event with a lot of tracks. But with this sort of modified sum, you can essentially veto the pilot vertex and then end up choosing your sort of, you know, soft, in this case, VBFX invisible vertex. And the performance is summarized in the plots on the, you know, at the bottom of these of the slides. On the two plots on the lower left are what we expect to see given the current geometry of the Atlas detector, where the tracking is limited to a rapidity 2.5. And so in this case, so the plot on the left, extreme left there, the ones where we have the black and blue lines, the new method is shown in blue, and you can see that it improves. So there's an average improvement of 8% on top of the current method, which is shown in black. But there's also like this correction of the slope of the black line, which is exactly this effect of pilot merging, and we're completely rectifying the effect of pilot merging because of this, you know, the idea of only looking at tracks that go into jets. So that's a significant improvement over the current method already. But then if we further, you know, only restrict ourselves to events where, you know, our forward jets have tracks in them, so I say forward, but I actually mean marginally forward jets, then we see that the improvement of this new method is actually all the way up to 98%, which just reinforces the idea that actually most of the inefficiency that remains is actually coming from the fact that we don't have a tracker that goes all the way out to 8 to 4. And that's sort of further, you know, our confidence in that statement is further justified when we look at the HL-LHC scenario. That's shown on the right, the lower right plot, And here we see that, okay, this new method, with that extended tracking acceptance actually has a selection efficiency all the way up to 98, 97%, which really means that the selection of this, in the case of VBA Higgs invisible, is essentially solved by sort of moving to this modified primary vertex selection scheme. Yeah, actually, that's all I have to say. It's a fairly brief summary.
Okay. Thank you. And the final one before we take questions is actually a poster, so people probably haven't seen that in the session. Xenmin, do you want to just talk us through? Please turn on your mic.
Yeah, sure. Sorry,
Hi.
I can go back to myself. Yeah.
Sorry.
Yeah.
I touched the keyboard.
Okay. Yeah, that's okay. Yeah, so the idea is that in current FC searches, the traditional new physics searches rely on hypothesis testing, and we use that hypothesis to design a trigger, and then if the event not being triggered will be discarded forever. So the worry is that maybe we already veto lots of new physics in the trigger level. The proposal is that whether or not we can implement a model agnostic trigger for the anomaly events, and we want to deploy a level 1 trigger to avoid any bias from the upstream. And here we explore the model using autoencoder to learn the feature of the background data, and then all the event with the loss function, which is defined between by the difference between input and output from the autoencoder. If the extreme loss value, we'll consider as an anomaly event, and then use that to select the signal that we're interested in. So, so here what we have is that a model using the CMS level 1 trigger input with 200 pileup, and we have a simple A-layer autoencoder and train it and with a purely background, and then we inference in the signal. And as you can see from the plot here, that it shows the separation power of the signal in the inference. And we were able to implement this model into the FPGA, which still fit into the resource and latency requirement of the CMS level 1 global trigger. So in summary is that we showed that a simple autoencoder model can be implemented at level 1 trigger for the anomaly event triggering at 40 megahertz. So one concern is that the online could be noisy, but then we found out this autoencoder trigger tend to be can tolerance certain noise, and we can also stabilize the trigger rate with some additional logic in the FPGA. So this study will be further documented into our phase 2 level 1 trigger TDR. So stay tuned.
Very interesting. Thank you. Okay, so let's take this set of talks and go over them in order. So Joe, can you come back? I think, David, are you still there? Otherwise, I'm going to ask his question because he said.
Yeah, I'm still here. Everybody was fast this time. So yeah, sorry, I have to leave at 6. That's why I was sending Marcus a mail. No, Joe, I had it's sort of off topic for your talk, but the data movement you're talking about for SPHENIX is on a scale of 2022 or 2023 pretty big compared to other things Brookhaven is doing, as far as I know. Is that the bigger sort of computing challenge?
Yeah.
Sort of data movement versus CPU.
So one of the challenges that we are facing and having to address is that we plan on processing all of this data at Brookhaven. So we are using the what was formerly called the RIC Atlas computing facility at Brookhaven to process all of our data. So we obviously share these resources with Atlas, so it's not like we have just one one computational center that we get to use, and we also share it with the STAR experiment at RIC. So that's one of the major challenges that we are going to have to address, and that's why getting our reconstruction time down to more reasonable numbers is so important, because we don't want to take 5 years to process all of our data before we can start analyzing it, that would be not very useful.
Yeah, definitely. Thank you.
I had a question. I mean, in your talk, you talked about a design problem to deal with TPC information in ACTS, and I didn't quite get that. I mean, it's the kind of old-style multi-wire proportional chamber TPCs. I mean, that seem to get away with these kind of surface ideas which are regular. And why isn't that the case for your TPC? Is that because of it uses gems, or what's going on there?
That's right. Our TPC is a continuous readout TPC with gems. So we basically have a continuous volume of gas in which you can identify clusters in any sort of space in that volume. So, ideally we would have, maybe set up some cylindrical surfaces, some concentric cylindrical surfaces, which would be very conducive to ACTS. But the fact that we don't a priori know where those surfaces will be, and also I don't know if you were able to hear the Elise talk that was I think the next day after mine, but there was a significant discussion about space charge distortions in the Elise TPC, which
I worked on Delphi TPC analysis. I can tell you something about space charges. Yeah.
Okay. Yes. So part of our issue also is that we will have significant space charge distortions as well that we'll have to address. So where we actually find clusters is not necessarily where they actually were.
Okay.
So we have a lot of sort of moving pieces, if you will, in our TPC that is not at the moment is difficult to implement within ACTS.
Yeah. I mean, and I think I realized. I mean that in the kind of Atlas-inspired surface model is probably not the most suitable.
The static surface model is probably not the ideal approach. It is also not for Bell 2, which has this sort of twisted geometry, which is not very easily to describe in a static navigation scheme. There actually will be a dedicated discussion in a few minutes on that from the ACTS developers with the collaborators. And without preempting anything of that one, I can't even join there due to other commitments. We're thinking of having a model, since what you saw in Xiaokong's talk, the propagator has plug-in mechanisms. So if we write a plug-in that can be fed in every track fit, for instance, with the measurement descriptions, and the propagator is able to stop at the given prescriptions, then we think we can solve this problem without forcing to create surfaces. But next, connecting the dots, hopefully with a full-fledged out model running already in SPhoenix.
Okay. Are there other questions for this talk? Joe, I think we don't have that, so.
All right, thank you.
Yeah, you're welcome. Okay, so then let's move on.
All right.
So hi. Thanks for turning on your camera.
All right.
So are there questions for this talk? I mean, I don't have one. I mean, this thing seems to be really what everybody was thinking of, that there's some PTs. I mean, it's really poor man, and somebody should do something better. And then you took the initiative to actually do something about it.
Yeah.
This idea being generalized. I mean, because I mean, fundamentally, this sum PT square. I mean, I haven't seen the rest of the event. Is a little bit stupid. I mean, do you think there's scope for generalizing this?
Yeah, that's a really good question. So sum PT squared essentially does really well for a good variety of final states, simply because most of the final states actually are fairly good in terms of visible PT. So there's good separation between them and what you expect from background. It's only an issue with certain final state topologies that are known, that have fairly low visible PT, where something like this wouldn't be needed. So to make a case for something that would be more generalizable, I think one could certainly make this generalizable, but you could argue that it's not needed, right? So this would be something perhaps more suited towards specific examples of things where some PT square would fail, because you could argue that, well, we don't need this in a general setting in the first place. But yeah, we are pursuing, we're sort of investigating the possibility of having a generalized version of this. So you could, work with the topologies that have something beyond just calorimeter jets. You could accommodate for leptons and so on and so forth. But yeah, whether we really need that or what the magnitude of improvement in that case would be on top of some PT squared is something that we want to see if it's even worth doing.
In your technique, then, are you checking? I mean, if the jets are actually the ones which triggered, or is there's no such correlation to trigger information?
Yeah, no, there isn't any such correlation. Yeah, exactly. That's a good point. There isn't any. We actually look at all the jets in the event.
Okay. Are there other questions from other people to the talk? People seem to get tired. Yeah, we are actually past our normal time, but that's fine. I mean, discussing is fun. So let's see if there is something else coming up. Doesn't seem to be the case. Nope. Thanks very much.
Thanks.
Okay, ciao. So then the poster, Sen-Ben, can you turn on your camera again? So this poster is open for questions. I should actually get it up. I mean, this thing on the HH24B is really impressive to see. I mean, what are the inputs which you are using there? Is this making use of the level 1 tracking information, or what is it?
Yeah, so for the phase 2 upgrade of CMS trigger, we have the tracking information. So then we were able to construct the particle flow candidates at level 1. And we also applied this puppy braid to mitigate the pileup. So the input for this autoencoder is using the puppy jet MHT, or hadronic component of the event.
So then, I mean, let me understand. I mean, this is the jet information coming from the calorimeters, not jet information coming from the tracker.
Both. It's called particle flow jets. So in the level 1, we combine the tracking with the calorimeter to form particle flow objects.
But you're not making use of any impact parameter tagging or whatever implicitly, or you're feeding in impact parameters that your autoencoder could actually become sensitive to these kind of ideas now.
No, there's no impact parameter. We don't have the displaced vertex. It's just purely the kinematic of the jets.
Wow, that's impressive.
So maybe I can follow up. No, go ahead.
Go ahead, Katerina. No, you were waiting.
Everybody's raising hands. I don't know who was first, actually.
Katerina was waiting in the chat. She was.
Oh, don't worry.
I
didn't even have but I forgot to have the hand, so I don't know if that.
Go ahead.
I guess it's a follow-up to Marcus. So I have two questions. One is the kind of you're saying that you're going to do this at level 1. So what are the input rates that you need to do something like this from the tracking? And do you do a pre-selection for trigger and then you apply the tracking for the calorimeter and then you apply the tracking, or you just put everything at the same time into the network? And then the second question is how much noise you expect, like things that the plus others is interesting to me. How do you deal with the plus others in this scenario?
Okay, so for the tracking, because this is the phase 2 trigger, so the tracking is reconstructed every 40 megahertz is CMS level 1 trigger. So we get the tracking information, basically at 40 megahertz, and then we further construct the jets with the check information. Sorry, what's the second question? The noise?
So you're
right?
saying that you're going to have to be able to read out the full tracking at 40 megahertz.
Yes, that's the part of the
Okay.
CMS level 1. Yeah.
Okay.
So in terms of array, it's kind of I think this is going to be studied more carefully in the future to see what's the bandwidth we can have in terms of the level 1 trigger rate of CMS. For phase 2, we have a 750 megahertz of level 1 trigger rate. But then, yeah, it's kind of we need to study more carefully how is the anomaly trigger rate overlap with the other trigger rates. So become
Yeah, my question was more about how the detector defects or things that you don't expect pop up in these tails.
Yes. So yeah, this is the common issue we have with autoencoder is that it's hard to distinguish the new physics from the noise. So from this model we trained, we find out that the autoencoder is not very sensitive to like 1 sigma variation of a single jet PT or eta. But if the whole event vary by 1 sigma, then it will see a sudden increase of rate from this autoencoder. So one way to deal with that is that in the trigger level, within the FPGA, we can add additional logic to map the trigger threshold of the autoencoder by dynamically adjusting by the trigger rate. So this can be achieved so that you're not triggering a fixed threshold. For example, on the left plot here, the threshold is not being fixed anymore. You can just dynamically adjust it so that you can always fix the trigger rate to a certain level. And then after you select the events, maybe in the offline, you need to be more carefully study the event selected, whether or not the new phase lie or really come from certain noise. Unfortunately, we cannot deal with that on the online level.
Right, yeah, but that is clear. So you plan to do cleaning afterwards, essentially. That is what you're...
Yeah, well, I think it's inevitable. I think the more advanced model of autoencoder is that you can train your autoencoder with the data that injected with noise, right? And then in the training, you can further constrain your autoencoder how much sensitive to a certain, typical type of noise you expect. This is still ongoing study.
Thank you very much. That answers my question.
David, thanks.
Yeah, I had some question on the input, and which is not completely clear. So what do you give as input? You have the jets, you have a list of n jets, eta phi, PT, or what do you give?
Sorry, yeah. So in this model, we have 18 inputs, with the missing ET and missing HT, the 2 of it. And then we have 4, I think we have 6 jets. There's leading 6 jets as input.
Leading 6 jets.
Event. Yeah, and the PT.5. That's 3 information we have.
Okay. Okay, and there is no attempt to. Okay, and then there is only 5 jets. You take 5 jets. Yes. Okay. Okay. Thank you. That was my remaining question. Thank you.
Okay, and I think I saw in between some other hands raised, which are lowered by now. Is there any other questions? No? Okay, thanks again to the speaker. And now I need to do a bit to change Hello, are people still there? Hello?
Yes, yes, we are there.
Yeah.
And Zoom crashed on me. Did it crash on you as well?
No, it stayed open.
Wow.
Yeah,
I mean,
I think a lot of people thought it was over.
I mean, it took me a bit of time, and I had to restart Zoom twice in order to get back in. I'm very sorry for this. Yeah, that's that's a bit of a bummer. Did you go over your talk, Daniel?
No, I didn't. I just wanted to see what you were.
Yeah,
planning.
yeah. I'm sorry for this. You uploaded your talk, or can you try to share it yourself? Because I don't trust my network connection, to be honest. I mean, it seems to be. I had problems with my network connection before the meeting, and it seems to come back. Is it okay that I turn off my video, because I really don't want to get kicked out of the meeting again?
Yeah, sure. I'll share.
Okay.
That should be visible, right?
Yeah, it's okay.
Cool. All right. Yeah. Sorry, I screwed up the Zen flow of the presentations, and maybe a lot of people thought
okay.
the presentations were finished, so they've left. But anyway, that's good. Fewer questions, maybe. So our the Exatrix group at Berkeley, anyway, we've been working on this pipeline for taking TrackML data and producing either seeds for more traditional techniques, Kalman filters and whatnot, or kind of an end-to-end track labeling that can give you a TrackML score. So we embed the TrackML data, which you would have seen in Nick's talk, into a learned embedding space, which is able to filter out the best set of candidate doublets, which is constructed into a graph. The graph is trained on a GNN, an attention mechanism, GNN message passing structure, and gives very good results, you know, mid to high 90s in percentage purity and efficiency. We then convert that into a triplet graph, which takes combinations of doublets and assigns them, combinations of hits. So a doublet becomes a node, and then the connections between doublets are the triplets, and they're classified with a score. And that gives even better performance, as you would expect, because it's using information from the previous step. And then we either apply some cuts on those triplets to get some very highly pure sets of seeds, and quite efficient at high PT. Or we can run some clustering mechanism on those triplets, and in this case we use DB-scan on the graph, and once we throw out some kind of unfair hits, we get quite a good TrackML score, which is corresponds to a well-labeled graph. Yeah, so that's all I'll say for that.
Okay, thanks very much. This talk is open then directly for questions. Do people have questions on it? I mean, I do have one. I mean, since you're using the TrackML datasets, I mean, where would this thing be in terms of the score? And there was also the comparison in terms of CPU time. Do you have a feeling for that, where you would end up with your approach?
At the moment, our per event is about 5 seconds per GPU. and we're able to parallelize that across N GPUs. There are a lot of low-hanging fruit for this speed up. We know we can get mixed precision implementation for at least the embedding, and I think we should be able to do the same thing for the GNN. That's early results on that from Nick are looking at like a double speed up, so down to less than 2 or 3 seconds. And there are still quite a few optimizations. So this is basically a proof of concept pipeline, and then the performance is definitely one of the next things we're looking at speed-wise.
Mm-hmm.
The dream would be sub-second, fully from to event data, hit data to labeled tracks or seed.
Mm-hmm. Okay. Any other questions from other people?